So this is going to be the case. Well, actually, let me classify things this way. We can say case 1 is the case where all the h's are 0. And then there are just no linear terms at all. The only terms in the equation are quadratic terms. The whole equation just reduces to something like this. Okay, and so here you see that I've just rewritten the equation. Okay, maybe I should avoid that. I'm going to stay with the same notation. Okay, so keeping the same notation as before, I'll have all of these terms, and then just the q on the other side, no linear terms. Okay, so this still has to be broken down further because if, let's say, all these lambdas are positive, then you'll have one thing that's going to be called an ellipsoid. If all of those lambdas are negative, okay, that's also an ellipsoid. Actually, it depends on q. Okay, so if q is positive and all of these lambdas are positive, then you can just divide through by q, and you'll get a 1 on this side. And that's like the standard form of an ellipsoid. Just and in fact, the positive coefficients, once you divide by q, so I'll have a term like this, for instance, right? I can take this positive number and just write that in the form 1 over a1 squared. And, you do that by just defining a1 to be the square root of this reciprocal. Okay? So then this term gets written in the form u1 squared over a1 squared. And the next term will be u2 squared over a2 squared. Right? And then you'll have a 1 on that side. That's like the standard form of an ellipsoid. Okay? But to classify further, under case 1, we have to look at the breakdown of how many of those lambdas are positive and how many are negative. Right? We also have to look at the sign of q. Also, q could be 0, right? It could happen that q is 0, and in that case you'll get something different, not an ellipsoid. You only get an ellipsoid when the q is non-zero, and then the signs of all the coefficients come out positive after dividing by q. Right? What do you get in other cases? Well, we'll look at that soon. Okay. But case 2 is where... Oh, so I really should mention one more thing about case 1, which is simply that this now is just an equation in R space. So we're treating this as the equation of quadratic hypersurface in R space, not in D space. And the way you get back to D space is by taking this quadratic hypersurface in R space and then just dragging it with respect to all of the missing axes of D space, like the V1 axis, the V2 axis, et cetera, and then the Vd minus R axis. So we basically have some lower dimensional quadratic hypersurface that we're going to try to understand the shape of by analyzing the signs of those lambdas and all the different behaviors that are possible. Right? But then once we do understand that shape, we still have to go through the process of, at least mentally, thinking that we've taken that R-dimensional set and kind of dragged it parallel to the V1 axis, and then taken that resulting set and dragged it parallel to the V2 axis, then taken that resulting set and drag it parallel to the V3 axis, and so on, until you exhaust all of the V's. And that will give you the original D-dimensional set that we're looking for, the capital V. Right, so this solution set here, this set of like U1 to UR, satisfying that equation, is not the set V. Rather, once you take that set, let me call it something like V tilde, okay, that's a subset of R space. Then you take that and you have to do that procedure where you drag it parallel to one of the V axes, V1, then take that, drag it parallel to the V2 axis, and so on. Okay? Then you'll get a set in D space, which is the original V, the original capital V. Okay, so I wanted to make that clear. All right, but case 2, we could say that some HJs are non-zero. Okay, and I claim that in this case, there is a rotation of the V subspace. Let me call it that. What I mean by that is the D minus R dimensional space spanned by the V's. Well, in the original D space. Spanned by the V1, V2, Vd minus R axes. Okay, remember that we've labeled the axes. Some of them are U1, U2, and so on, and then the rest of them are V1, V2. So just look at the D minus R dimensional subspace spanned by, the V1 axis, the V2 axis. Okay, but anyway, so we're just rotating in that space, leaving all the other axes fixed. The complementary U subspace fixed. Okay, after which, so after we perform that rotation, just in case it's not clear what's going on, let's look at something an example in 3 space. You see, in 3 space, I can perform a rotation in the xy plane, for instance. Just do a rotation in the xy plane. And then just leave the z-axis alone. That's the complement, orthogonal complement of the xy plane. Right? So we have the xy plane, and then the z-axis is its orthogonal complement. So basically any vector along the z-axis is left fixed, but any vector purely in the xy plane is rotated in some way by this rotation. But you see, then that affects a rotation of all 3 space, where basically just any point in 3 space, you can project it onto the xy plane. That will be subjected to a rotation, moving here, and then you can just move that up by the same distance. So points will sort of move around cylinders parallel to the z-axis. So you can specify a rotation of a higher dimensional space by specifying a rotation of some subspace of it, lower dimensional, and then keeping the complementaries, like the orthogonal complement, fixed. So if I rotate in a plane in 3 space and keep the orthogonal line fixed, that affects, again, a rotation of the original 3 space. Right, so that's what's going on here. There's some rotation that we can do in some lower space, lower dimensional space, just among the v's, while leaving the u's, those axes, fixed. That's the orthogonal complement. And the reason it's the orthogonal complement is because these axes are all mutually perpendicular, and disjoint. So you have like the set of the v axes, and then the disjoint set of the u axes. And since all the axes are pairwise perpendicular, obviously, right, the span of the v axes is exactly the orthogonal complement of the span of the u axes. So we can achieve a rotation of d space by just doing a rotation among the v axes and leaving all the vectors in the pure u directions, or any linear combination of the u directions, fixed. Okay, well anyway, after we perform this rotation, what happens is essentially only one non-zero linear term remains in the equation. Okay, the equation then becomes like this. You still have all the same quadratic terms because I didn't touch the u's. But now there's only one linear term, and we can write it on the other side of the equation. Okay. In fact, sorry, let me just give myself a bit more room here. I'm going to move the q, the constant, to the other side, and I'll write the linear term on this side. And then there's going to be, like, this linear term is going to have a coefficient. And I want to divide through by that coefficient. It's going to be a non-zero coefficient. Yeah, so whatever that coefficient is, let me say that it's like 1 over alpha times some variable. Now, this variable is not actually one of the v's. It's some combination of the v's, because some rotation of the v's has been performed. So it's actually going to be some sort of combination of the v's. But I want to give it its own name. I'm going to call it just w1. Okay, and then I can put the alpha, I can multiply through by alpha just to get it in a nice kind of standard form. Okay. So that alpha is just going to sort of distribute and modify all the rest of the coefficients. And this alpha is non-zero. So you can just distribute that. All the rest of the coefficients will be modified. All right. So what does that look like? Let me just illustrate in 3 dimensions. Okay. So let's say we have an equation where z appears quadratically, but x and y both appear linearly. Right, so let's just say I have like 2x minus y, and then I have plus 3z squared equals 5, something like that. We want the set of all solutions in 3 space of that equation. So both x and y appear non-trivially in the linear terms, and then you have a disjoint set of, remember we have these disjoint sets of variables, some of which appear in the linear terms and the others of which appear only in the quadratic terms. So in this case, the disjoint sets are x and y, form the ones that go into the linear terms, and then z is the other set by itself. Okay, so what's going to happen is we're going to perform a rotation of the xy plane, basically creating a new set of axes in that same plane. You know, let's say x tilde, y tilde, whatever. And these 2 linear terms are then going to combine to give something like 1 over alpha times x tilde only. In other words, y tilde can be eliminated. Any mention of y tilde can be completely eliminated. So in other words, the resulting set is then cylindrical with respect to y tilde. X tilde appears in the equation, but y tilde does not. So when you write the resulting equation in terms of those 3 variables, that is x tilde, y tilde, and z, when you run, and those are still perpendicular. These are all mutually perpendicular. So in that coordinate system, the equation is clearly cylindrical with respect to the y tilde axis. And you can understand the equation by just looking in the x tilde z plane. Right? And in that plane, what does the equation look like? Well, let's just, okay, so I have to work out what the 1 over alpha is, of course. But you see that equation is like, it's a parabola, because essentially you have x tilde expressed as a quadratic function of z. If you move the 3z squared to the other side, you'll have exactly x tilde isolated by itself on one side, and then on the other side you have some quadratic function of z. So you'll have a parabola basically in the x tilde z plane. It's going to be a sideways opening parabola like this, because you see that it's the x tilde that's expressed quadratically in terms of z. So it's kind of like a sideways opening parabola. Anyway, that is then going to be dragged in the y direction, giving a cylindrical set. Okay, so that's the idea, is to basically rotate the coordinate axes, but just among the v's, which are the ones involved in the linear terms. So basically the v variables are going to become the w variables. I'm going to take the span of the v's and rewrite, like find new axes for that space, which are the w's. Same number. Like in the example I just showed you, the original v variables were x and y, and then the w variables are x tilde and y tilde. It's like a rotated version of x and y. The span is the same. They still span the same plane. But you see that one set of axes results from the other by rotation. And in terms of the w variables, what's going to happen is only w1 is going to appear. Only w1 appears. The rest of the w's do not appear in the equation. Okay, so what's going to happen then is like the set is going to be basically parabolic with respect to w1, because w1 is expressed as a quadratic function of some other variables. And then in all the remaining w directions, like w2, w3, you have a cylindrical set. So what you do is you can think of this equation as acting in like r plus 1 dimensions, because you have the original u1 to u2 up to ur gives you r mutually perpendicular directions, and then w1 axis is direction number r plus 1, and that's also mutually perpendicular to the u's, because remember that the span of the w axis is going to be the same as the span of the v axis, and the span of the v axis is perpendicular to the span of the u axis. So the w1 axis is still perpendicular to all of the u axes. So you have r plus 1 mutually perpendicular directions. And as an r plus 1 dimensional set, we can try to understand the geometry of it. It's going to be parabolic with respect to the w1 axis, in the sense that the w1 coordinate is just a quadratic function of all of the other coordinates. Okay, so cross-sections are going to be like parabolas. If you think about cross-section where, let's say, you set u2 equal to 0 and also u3 equal to 0, or it doesn't have to be 0, just any constant. If you set u2 equal to a constant and u3 equal to a constant, and then just consider the equation in the u1, w1 plane, that's going to be the equation of a parabola. Okay, similarly, in the u2, w1 plane, you'll get a parabola, possibly a different parabola, and so on. Okay, so yeah, that's like a parabolic set with respect to w1. Let me write this down. So in r plus 1 space, this is parabolic with respect to the w1 axis. All right, and then you still have to take that parabolic set and like drag it in the remaining directions, the w2 direction, then take that result and drag it in the w3 direction, and so on, until you get the full d dimensions. Right, but at least we understand the geometry of it. Well, of course, we still have to study what parabolic sets can look like. Familiar examples of parabolic sets. Well, think of something like this, and think of something like this. Okay, so you see here that these are just two examples of this general form down here, because you have some quadratic terms with non-zero coefficients, and then on the other side of the equation you have a linear term with respect to a different variable. Okay, so here, like, you have a linear term with respect to z, and then quadratic terms in x and y. Same here, linear term in z on one side, and then on the other side you have quadratic terms in x and y. There could also be a constant term here, but I'm going to keep things simple by ignoring the constant term. So what do these sets look like? All right, well, if you look at this one, setting y to 0 gives the parabola z equals x squared, which looks like this in the xz plane. Right? And if you set x equals to 0, then you're in the yz plane, and you get a parabola z equals y squared. So that's a parabola like this in the yz plane. And then also if you set z equal to a constant, like let's say I set z equal to, I don't know, 4, right? Then you get the equation of a circle, x squared plus y squared equals 2 squared. Circle of radius 2. So with positive heights, when z has a positive value, you'll get circle cross sections. And of course, if z is negative, like if I set this to -1, then there are no solutions at all. You'll have empty cross section. But you see what the result is, that you get this bowl-shaped object. It's like it goes up forever, but it has these circular cross sections. And it didn't have to be a circle. It's only a circle because I chose the two quadratic terms to have the same coefficient. I could have had something like this, for instance. And then it would have been an elliptical cross section. But anyway, that is like an elliptical paraboloid. It's a paraboloid with elliptical cross sections. But notice that it is parabolic with respect to the z-axis, because the z appears linearly. And what this reduction here is doing, this reduction where I can do a rotation among the v's, certain rotation among the v's, right? What that's doing is, that is just making sure that the set is parabolic only with respect to one variable. The set can't be parabolic with respect to more than one variable. It just ends up being cylindrical with respect to all the other ones. See, it's parabolic with respect to W1, but it's then going to be cylindrical with respect to W2, W3, up to WD minus R. So it just turns out that by nature, the set can't be parabolic with respect to two different variables. It can only be parabolic with respect to one of them. Okay, and actually don't forget that these are not the original variables. When I say it's parabolic with respect to W1, this is after performing a rotation of the axes, so that I have new axes, essentially. Okay. So in other words, they don't have to be the original axes. You might have a situation where a set is parabolic with respect to some direction of space that was not one of your original axes. It's only after performing rotations that you make it an axis. Okay. What about the second equation here? So in that case, you see that, okay, we've actually done this in class already, so I can skip ahead and just take you to the answer. Remember that in this case, we had an upward opening parabola in the xz plane, but a downward opening parabola in the yz plane. And the cross sections are hyperbolas. And so you get this saddle-shaped surface. Something like that. Okay. And we call that the hyperbolic paraboloid. So notice it's also a paraboloid because it is parabolic with respect to some direction of space. Namely, it's parabolic with respect to the z direction. What does that mean? It just means that z is expressed as a quadratic function of the other variables. Okay. Good. All right, now neither of those is cylindrical with respect to any direction of space. You can see that both of those sets that I just drew do not consist of like unions of parallel lines. So they're not cylindrical with respect to any direction of space. Okay, but we've already seen an example. Where was it? Yeah, this parabolic cylinder, right, where it actually is cylindrical with respect to some direction of space, namely the x direction. Now notice that the parabolic cylinder, you can have a parabolic cylinder that's cylindrical with respect to some other direction. It doesn't have to be an axial direction. You can imagine just having some random direction, and then you have parabolas coming off of there. It's only after the rotation of the axes, so that you perform a rotation in the xy plane, so that maybe the x-axis becomes or moves onto that red line. And then with respect to that new coordinate system, the set will be cylindrical with respect to one of the axes, namely this red axis. Right? But it's still perfectly possible to have a parabolic cylinder where the cylindrical direction is not one of the axes. But in that case, you have to perform some rotation in the xy plane in that picture to write it in standard form. Okay, so yeah, neither of these sets is cylindrical. But what was my point? My point is that, yeah, this parabolic cylinder, let's take a careful look at it. So it's cylindrical with respect to the x-axis. Now, is it parabolic with respect to a certain axis? Yes. It's parabolic with respect to the z-axis. You see, because z is being expressed as a quadratic function of some others, namely y. So what you really have is there's a certain two-dimensional parabolic set. There's a certain two-dimensional parabolic set, which is this yellow parabola. And then that is being dragged in some third perpendicular direction, namely the x direction. Okay, so yeah, you can have sets, you can have these quadratic hypersurfaces that are cylindrical with respect to some of the axes, and then parabolic with respect to some other axis. But it can only ever be parabolic with respect to one particular direction. just by the nature of things, quadratic hypersurfaces can only ever be parabolic with respect to a single direction in space. And then it will have to be cylindrical with respect to all the others. Well, all the other v directions. Okay, very good. So where are we now in our classification scheme? Okay, sorry, I was called away. I don't remember exactly where I left off. But the thing we need to do now is we need to prove this claim. Right? This claim is a kind of theorem that there exists a rotation that will do this. And we need to prove that. But before we do, let me just emphasize a couple of small things. Okay, one small thing to emphasize is just that in the resulting equation, right after we perform this rotation, we're going to get an equation that looks like this in the red box here, where basically one variable, w1, is expressed as a quadratic function of u1, u2, etc. up through ur. So we can view that as quadratic hypersurface in r+1 space, as I mentioned before. Right? That's what I'm saying here. And to get something in D space, we would then, take that object in r+1 space and drag it parallel to various axes, the W2 axis, W3 axis, and so on. But one thing we should ask ourselves is, what exactly does it mean in very precise terms to say that this quadratic hypersurface is parabolic with respect to the W1 axis? Okay? So I want to just state a definition of that, and I'm not going to even bother writing it down. I just want to make sure you understand it. The definition goes like this. It's just that if you substitute some constant for every one of the u's except for one of them. So what that involves is, for example, let's say I set u2 equal to some constant, say 5. I set u3 equal to some constant, let's say pi. Set u4 equal to minus radical 7, whatever. Okay, but I leave over u1. I don't touch u1, so u1 still remains a variable. And so what that corresponds to doing is taking a kind of curve of intersection. Let me explain. Okay, in this r+1 space, when I set, say, u2 equal to some constant, what does that look like? I have the u2 axis, and I fix some constant, like some point on that axis, and I'm restricting attention to just the points that have that particular u2 coordinate. Well, that's a kind of hyperplane. In r+1 dimensions, that would be an r-dimensional hyperplane, perpendicular to the u2 axis. Okay, so for an example, just think of 3 space. If I take, let's say, x equals 1 or something in 3 space, here's what that equation looks like. You take the point 1 on the x-axis, and you consider all the points in 3 space that have an x-coordinate exactly equal to 1. And what you'll get is a plane, 2-dimensional set, which is parallel to the yz plane, but 1 unit away from it. So it happens to be a plane in that example, but in general it's a hyperplane. It has dimension 1 less than the ambient space. And in our example, the ambient space has dimension r+1. Okay, and then let's say I set u3 equal to a constant. So that is also an r-dimensional hyperplane, but those two hyperplanes are perpendicular. Like the u2 hyperplane, u2 equals a constant, and then u3 equals a constant. That's 2 perpendicular hyperplanes, both of dimension r, in r+1 space. But their intersection will have dimension r-2. Just like, if I take 2 perpendicular planes in 3 space, like think of this picture. I have the blue plane, which is sort of vertical like this, and then I have that green plane. But their intersection is a line. Okay, and then you have to keep doing that. It's like you do that for the u2 equals a constant, you do that for u3 equals a constant, u4, up to u sub r. So what you're getting then is like some flat object of some dimension in r+1 space. So within that flat object, in other words, okay, when I say a flat object, I just mean a subspace, but possibly translated so that it doesn't necessarily go through the origin. You take some subspace, which does have to contain the origin, and you translate the whole thing. So let's call that a flat object. It's also called an affine subspace. That's a very fancy term. I prefer the term flat. So a flat is like a translated subspace. Anyway, within that flat, you will then have the equation w1 equals, so let me write it maybe over here somewhere. You'll have like an equation of the form w1 equals some constant times u1 squared, and then plus some other constant. Because I've set u2 to some constant, I've set u3 to some constant, right, and etc., and then ur to some constant. So, okay, the flat that I'll have left is like a 2-dimensional flat, because the only variables left are u1 and w1. So basically the space spanned by those 2 axes in the original r+1 space. Just take those 2 axes, the w1 axis and the u1 axis. That's like the flat left over, once I set u2 to a constant and u3 to a certain constant. Okay, within that flat, that's the equation of a parabola. That's a parabola familiar from 2-dimensional geometry, because this is in a 2 flat. That is, you have 2 variables, u1 and w1, so which are, again, 2 mutually perpendicular axes. Okay, so essentially that just reduces to familiar 2-dimensional geometry. And we know what that type of equation looks like. We know that it's a parabola. Okay, so, and then the same would be true if I set, let's say, u1 equal to a constant and u3 equal to a constant and u4, but I skip u2. See, in that case, you would get basically the same type of equation. It would be something like, well, let me call it c tilde, u2 squared plus k tilde. Right, the constants there would not be the same, obviously. C tilde and k tilde would not be the same as c and k. But the point is you still always get a parabola in every one of those flats. So essentially, if I take the W1 axis, this is what I'm saying. If I take the W1 axis together with, let's say, the U1 axis, I'll get a parabola. That cross-section of the object is exactly a parabola. Okay. But if I take the W1 axis together with, let's say, the U2 axis, that's also a parabola, just possibly a different shaped parabola because it has different coefficients. And if I take W1 with U3, that's a parabola, etc. And if I take W1 with UR, that's a parabola. So every one of those cross-section families gives parabolas. And because of that, we call such an object a paraboloid. But what kind of paraboloid it is depends on basically the signs of these lambdas. Right? We already saw an example of that in 3-space. I don't remember exactly where I drew it. Yeah, here, right? We have two different kinds of paraboloid in 3-space, depending on whether the lambdas are like both positive, or maybe one is positive and one is negative. Here, both lambdas are positive. But here I have a positive lambda and then a negative lambda. So, okay, the type of paraboloid will depend on the distribution of signs, plus or minus, to those lambdas. But I wanted everyone to understand very precisely what a paraboloid is. Okay, so when written in this standard form, with one variable isolated, it's basically a quadratic hypersurface in r+1 dimensions, such that for the W1 axis, with any other axis, U1 or U2, or when you look in just that plane, the W1 U1 plane, or the W1 U2 plane, or the W1 U3 plane. In all of those planes, the cross-sections are parabolas. Oh, not just in those planes, but all planes parallel to them as well. So it's not just in that coordinate plane. It's like any plane parallel to that coordinate plane. All of those trace families are parabolas. Okay, anyway, so coming back to this question now, how do I know that such a rotation exists? How do I find it? Okay, it's pretty easy proof. So it goes like this. Remember, we started with the assumption that we had some linear terms. So what was it? It was like h1 v1 plus h2 v2, and then h d minus r v d minus r. Those are just the linear terms. There were also the quadratic terms back here. And then we had a constant term. Well, I guess the whole thing was like set equal to a certain constant q. Let me just make sure that I'm remembering that correctly. Yeah, I think so. Yeah, this was the equation here. So now we're just like focusing exclusively on these linear terms right now. And remember, we're assuming that at least some of them are present. At least some of those linear terms are present. So assume, in other words, that h1, h2, up to hd minus r are not all 0. So we can form a vector out of them, h, which is of dimension d minus r. And what this is saying is that h is not the 0 vector in that space. So therefore its length is not 0. Its length is strictly positive. And if I factor out exactly the length of that vector, so leave the quadratic terms alone, right? And then I'm going to factor out the length of that vector. And then what's going to be left is like h1 over that length times v1, h2 over that length times v2, hd minus r over that length times vd minus r, right, equals q. And this is just some positive constant. So we can just like divide through by that constant, divide the entire equation through by that constant. And that's going to, of course, modify the coefficients in the quadratic terms, but it's not going to zero out any of those coefficients. It just divides every one of those coefficients by some positive number. So it actually preserves the signs. That's the important point. Dividing through by a positive number will leave the signs of those lambdas alone. These terms had like lambda j1, u1 squared, etc. Now those terms are going to become lambda j1 over norm h times u1 squared. But you see the signs of the coefficients are left unaffected by that. Okay, so yeah, and then what we have here is just the dot product of some unit vector with v. We can think of that as in that way, or maybe better as like a row matrix multiplied by column matrix v. So let me call that unit vector, what should I call it? Maybe I'll call it, let's say s. So it's like the dot product of s with v, or we can also write it as s transpose times v, a row matrix times a column matrix. So what I mean by s here is just the vector whose components are h1 over norm h, h2 over norm h, etc. In other words, it's the vector h divided by its own length, so it's clearly a unit vector. It's a vector of length 1. Okay, so the linear terms like reduce to that. Now, here's the thing. I can take that vector s, which is of length 1, and notice that this is a vector in d minus r space, because h, the original h was. And this is just the unit vector in the same direction as h. That's what s is. Okay. So what I can do then is I can take, extend the list s to a basis. Take the list of one element s, and just extend it to, in fact, an orthonormal basis. We know how to do this by the Gram-Schmidt process. Basically, you would just extend that list to a basis of d minus r space in any way that you like. So, here's how you do that. You just take any vector that's not a multiple of s and add it to that list. And then take any vector that's not a linear combination of those two and add it to the list. Right? And then once you have d minus r vectors that are independent, then you have a basis for d minus r space. And then you would just apply the Gram-Schmidt algorithm to orthonormalize it. Okay, so we know how to do that. And let's just call that basis, let's say we call the original s s1, and then we'll have s2, s3, and so on, all the way up to sd minus r. So these vectors are orthonormal. Okay, and we can also label them in such an order that the frame is positively oriented, like the frame, the ordered basis in that particular order is positively oriented. Right? So like when you label these, you're free to label them, to subscript them any way you like. You can list them in any order. It doesn't affect the orthonormality. The orthonormality is a geometric property of that collection of vectors. It doesn't depend on the order in which you list them. So you can just go ahead and list them in whatever order is convenient. And let's say I've labeled them in such an order that that frame is positively oriented. Remember, that just means that the matrix with those columns, if you make a matrix with those columns, its determinant is positive. Okay, so what I want to really do, though, with those vectors is I want to form a matrix with those as the rows, essentially. Okay, so let me form a matrix, say M, where I'm going to take S1 transpose as the first row, and then S2 transpose as the second row. Okay, all the way down to D minus R transpose as the last row. Right, notice that that's a D minus R by D minus R matrix. And I claim that it's more than that. It's actually a special orthogonal matrix. In other words, it's a rotation matrix. This M is a special orthogonal matrix of dimensionality D minus R. So it represents a rotation of D minus R space. Okay, why is that? Well, key is to look at the transpose. Like if we look at M transpose, that just has S1 as the first column, right? S2 as the second column, and so on. And we know that these columns are orthonormal by construction. And that means that we can conclude from that M transpose is orthogonal matrix. Remember, we've proved a while ago that a square matrix has orthonormal columns if and only if it's an orthogonal matrix. It has the property that its transpose equals its inverse. So what I'm saying here is, like, if I take its transpose, which happens to be M again, but it's the same as like the M transpose inverse. Okay, so the fact that it has orthonormal columns implies that it is an orthogonal matrix. But what about special orthogonal? Well, you have to remember that every orthogonal matrix has determinant equal to 1 or determinant equal to -1. But because we know that the determinant of this matrix, the determinant of the matrix M transpose is positive, that's what I said right here. So we know that it can't be -1. Therefore, in fact, has to be 1. So it is a special orthogonal matrix. It's an orthogonal matrix with determinant 1, and that means it represents a rotation. Okay, but of course the inverse of a rotation is also a rotation. We've already talked about that. And M transpose inverse is the same as M transpose transpose. In other words, M. Like we already noted that here. So that is also, therefore, a rotation, a special orthogonal matrix. Okay, as I claimed. Now, what's the relevance of that matrix M? Well, if I take that matrix M and I multiply by the vector V, so in other words, I'm looking at the linear map based on that matrix M, and I'm applying that to the vector V. So that just gives me M times V. So we know the rows of the matrix M. And then the way matrix multiplication works is that to compute this product, you're going to be just taking like the first row of this left-hand factor and combining it, multiplying it by that column. And then you do the same with the second row, and then third row, and so on. So what you're going to be getting here is exactly S1 transpose times V, and then S2 transpose times V, etc. Okay, but notice that that first entry is exactly what we had here in the equation. So let me just call the resulting vector W. W is like the image of V after a certain rotation. This is, again, a rotation not of D space, but of D minus R space. Just those V coordinates, the V1, V2, up to V sub D minus R. The U coordinates are not being touched. Right, so like this first thing is just W1, and then this next thing is W2, and then WD minus R. Okay, so you see that W1 is exactly this quantity here, which appears in the equation. This entire thing is simply W1, that entire term. Okay, and what about W2 and W3, and what are those? Well, they're just some combinations, but they're irrelevant because they don't appear in the equation. You see, W2, for instance, would be S2 transpose times V. So it's some linear combination of the V's. It would be like S12 V1 plus S22 V2 plus SD2, D minus R 2 VD minus R. Okay, where these numbers here, S12, S22, are just the components of this vector, or that row matrix. All right, well, we don't know what those numbers are, but it doesn't matter anyway. This variable W2 does not appear anywhere in the equation. Okay, so what we've done now is we've just gotten rid of all the V's in the equation in favor of a single W. W1 appears in the equation, but none of the other W's do. Okay, so you see that by taking that the V axes, remember we had the original D-dimensional space. We subdivided the axes into two groups. The first group of axes we called U1, U2, up to U sub R, and then the rest of the axes we called V1, V2 to VD minus R. Now, the space spanned by those V axes is basically a copy of D minus R space embedded in D space. And within just that D minus R dimensional subspace, we just performed a rotation where the V axes move and they become like the W axes, something like that. Well, we're really taking like the active viewpoint rather than the passive one. We're thinking of V as a vector in that space, and then we move it, we rotate it to become W. But it stays in that same space, that same D minus R dimensional space. And then the U axes are totally orthogonal to that space. Okay, and so we can put the two together in the following way. We can consider like a block matrix where we have the R by R identity in that corner, and then the matrix M that we just found in this corner, and then 0 blocks, like that. Okay, so let me just tell you the sizes of these blocks. This block is R by R, and this block here would be D minus R by R. This is D minus R by D minus R, and that's D minus R by R. Okay, so anyway, that total matrix, sort of out of names for things, but okay, maybe I'll just call it like capital N. Okay, that is a D by D matrix, and I claim it's also a rotation matrix. In other words, it's not just a D by D matrix, it's in fact a special orthogonal D by D matrix. In other words, it's a rotation matrix for the original D space. But you see, the fact that it has the R by R identity here in this block means that the U coordinates, which were the first R of the coordinates, are going to be left alone. See the effect of multiplying N by any vector where I put the U coordinates first and then the V coordinates next. We can work this out by block multiplication rule. You're going to get like I sub R times U plus 0V, and then 0U plus MV. And, you know, the identity matrix times U is simply U, and then you're adding a 0, and then this is M times V, which is W. So you see that the U coordinates are left alone, but the V coordinates get replaced by the W coordinates. And so we just have a new set of variables, essentially, for D-dimensional space. U1 through UR, followed by W1 through WD minus R. And that's achieved by a particular rotation. All right, now how do I know it is a rotation? Well, that's quite easy to see. If you look at N transpose, you can work out the transpose like block by block. You'll get the transpose of the identity there, and then M transpose here. And then these zeros will swap, basically. The two zero blocks will simply swap. But then if you multiply that by the original matrix N, you can use a block rule, and you'll see that you're just going to get the identity matrix and then also the other identity matrix of the other size. Because M transpose is the same as M inverse. But that's just the identity of size D by D. So N transpose and N are also inverses, which means that that's also an orthogonal matrix. And then it's clear that its determinant is 1, because when you calculate that determinant, you can do it by cofactor expansion, like along the first row. There's just a 1 in that place and zeros everywhere else. Then you can do the remaining minor by cofactor expanding along the next row, where there's a 1 in the first place. And then eventually you'll just boil it all down to the determinant of this block. Right? After using cofactor expansion several times, you'll see that it's the same as determinant M, which is already known to be 1. So indeed, N is a rotation matrix for the full d-dimensional space. Okay, so you see by doing one more rotation, if the equation has linear terms in it, if the equation has any linear terms with non-zero coefficients, that's the assumption we're making here. These coefficients of the linear terms are not all zero. In that case, there's an additional rotation of d space that we can find. Notice that it's based on those coefficients. It's based on these h's. You take all those h's, you find the norm of that vector, divide by that norm, that gives you the vector s, or s1. Okay, and then you just find s2, s3, and so on by the Gram-Schmidt process. That gives you this matrix M, and then you put that M in as a block in this formula here. That gives you the matrix N. And that matrix is a rotation matrix for the entire d-dimensional space. And that additional rotation will have the advantage of reducing the equation further to this canonical form. Lambda j1 u1 squared, etc. Well, actually now, okay, let me just make sure I'm being really accurate. Remember that I've divided by this norm of h. Times ur squared, and then we just have the single term w1, and then there's the q on the other side. Okay, so by isolating w1, of course I have to move all these terms over, all these quadratic terms. We can get the equation into this form, where basically w1 is expressed as a quadratic function of the u's. All right, now don't let these minus signs here throw you, because the lambdas can be either positive or negative. We don't know. So yes, you have to change their signs, but that just means changing positives to negatives, but also changing negatives to positives. So in the end, the equation can have any combination of signs. Okay, so yeah, that's how you deal with something that has linear terms in it. By making one additional rotation of d space, we can get the equation into that form, which is a form of a paraboloid. And it's also noticed that it's cylindrical automatically with respect to the W2, W3, WD minus R directions of d space. Right? And it's of course parabolic with respect to the W1 direction. All right, I should clarify what I mean. What do I mean by the W1 direction anyway? Right, so let me just clarify. Remember that we have coordinate axes that we've subdivided into groups, and the first few of them are labeled with the u's, and then the next ones are labeled with the v's. So let me just draw the picture in 3 space, and let's assume that the group of u's has only one element, which is, let's say, the x-axis, right? And then the y and z axes are the other group, which would be labeled v1 and v2. Okay, so when I say the v1 direction, it's clear what that means. It's the direction e2. It's like the positive y direction. That's what I mean by the v1 direction. It's the same as the y direction, but specifically it's this vector. It's like the unit vector e2. Okay, and when I say the v2 direction, what I mean is, you know, e3, which is the unit vector in the positive z direction. Okay. Now, what do I mean by the w1 direction? So you have to remember that in this subspace, the subspace of just the v axes, just the span of the two axes labeled v, within that space there was a rotation. That was the matrix M. We just rotated within that plane, leaving this third axis alone. But of course, by putting a block of the identity matrix and then a rotation here, right, we get a rotation of 3 space, as we just talked about. So we can regard the whole thing as still just like a rotation of 3 space, which is a rotation about this yellow axis. So it's really just things are moving about that axis cylindrically, or circularly, I should really say, centered on that axis. Okay, now under that rotation, E2 moves somewhere. Under that rotation, E2 is going to move. The vector E2, which was here, let's say, right, is going to rotate within that plane, and that rotated image is like m times E2. Well, it's really n times E2, because n is the 3 by 3 matrix. E2 I'm regarding as a 3-dimensional vector, or written as a column. It's that. And so if you take the matrix n, which was that rotation matrix, and just multiply it by E2, then you'll get like the rotated image of the V1 direction. And that rotated image is what I mean by the W1 direction. The W1 direction is just the rotated image of the V1 direction. Okay, under the rotation n that we just found. And similarly, the W2 direction would be the rotated image of the V2 direction. Because remember that that's how W and V are related. W and V are related this way. W is just m times V. And in the d-dimensional context, the vector u followed by w is the rotated image of the vector u followed by v, where the rotation now is n, this matrix n. Okay, so basically w1 is sort of, we're regarding it as a new axis. It's not literally one of the axes. That's why I'm trying to clarify. The y-axis is literally one of the axes of space, and that's the v1 direction. That's literally one of the axes of space. It happens to be the y-axis in this picture. But after that rotation, right, the vector e2, which is in the pure y direction, rotates here, right? And that's no longer one of the axes of space. I'm just calling it the v1 axis. Sorry, the w1 axis. I'm calling it the w1 axis. It's not literally an axis, but it's a direction of space, and we have a formula for it. It's n times e2. Okay, so that direction of space is one of the directions in which this paraboloid is cylindrical. No. Sorry, I just said the wrong thing. This is the w1 direction. That's the direction in which the thing is parabolic. But what's the w2 direction? So the w2 direction is just a shorthand that I'm using for the vector n times e3. Same rotation matrix n, but e3 is what I called the v2 direction, and the rotated image of the v2 direction is the w2 direction. So we know how to calculate that. We just know, we can find the matrix capital N and then multiply it by e3. So that's what I mean by the w2 direction. And that's some direction of space. It's not an axis, but it's the rotated version of this black vector here. So it's going to be like that green vector. It's somewhere in that blue plane, somewhere in the yz plane. But that direction of space is a direction in which this paraboloid is cylindrical. Now what does that mean? Okay, it means that if I drag the thing in that direction, the shape doesn't change. If I take the entire graph of this quadratic hypersurface and just drag it in that green direction, it will just go right back onto itself. There will be no change. So basically you can do any translation you like in that direction, and the overall graph will be totally unchanged by that translation. That's what happens with a cylindrical object. If you translate it along those parallel lines that make up that cylindrical object, there's actually no change in the graph at all. So it extends indefinitely in both directions. So the graph overall does not change under any translation in that direction. That's a way of thinking about it. This green vector here is such a vector. And there will be a number of these, right? That's the w2 direction, but there's also the w3 direction, and the w4 direction, and so on. Okay, so you see that there's only one parabolic direction, w1, and then the rest of those are automatically cylindrical. Okay, good. So I hope that clarifies what I mean by those directions of space. So where are we now? We now know how to deal with the case where there are some linear terms, there are some linear terms present. But I want you to notice that what we've done is we've basically reduced the whole problem to back to case one, where there are no linear terms. Let me explain. Okay, by reducing the equation to this parabolic type, sorry, where am I? Yeah, by reducing the whole equation now to this parabolic type, what we've done is we've basically taken the w1 direction out of the equation, or out of the problem, in addition to the w2 and w3, which don't even appear at all. Right? We know that since w2 makes no appearance, we don't have to worry about it. We understand immediately that we just have cylindricality in that direction. But also w1 can be left out of the analysis now, because we know what the cross-sections look like in, let's say, the w1u1 plane, and the w1u2 plane, and w1u3. Those are all parabolas. We can find the equations of them easily. The only cross-section family we don't understand is when we set w1 equal to a constant. Right? Let's say I set w1 equal to a constant. Well, if I set w1 equal to some constant, then that constant here can be combined with this constant q on one side of the equation. And then on the other side, you're just going to have all these quadratic terms. And that's exactly what case 1 looks like, just in some lower dimension. This would be in dimension r. You have exactly r quadratic terms with non-zero coefficients equal to some constant. So to understand the shape of that cross-section, which you get by setting w1 equal to a constant, right, you have to go back to case 1 and figure out, how do I figure out the shape if there's only quadratic terms? If I have a quadratic equation that has only the quadratic terms, only the pure square terms, set equal to some constant, how do I learn about the shape of that? That will tell us about the shape of the cross-sections obtained by setting w1 equal to a constant. Okay. Now what that looks like geometrically, you have to remember that w1 is actually some linear combination of the v's. So you can see it here. w1 is this linear combination of the v's. It's going to be like, s11 v1 plus s21 v2 plus s d minus r 1 v d minus r. Okay, so it's just some specific linear combination of the v's. And if I set that equal to some constant, what that gives me is the equation of some flat in d minus r space. See, if I take some specific linear combination of all those variables, v1 through vd minus r, and set that equal to a constant, that's a hyperplane in d minus r space. The graph of that is some hyperplane in d minus r space. In other words, it's a flat object of dimension 1 less. So that equation would be a hyperplane, or flat, of dimension d minus r minus 1, sitting in d minus r space. And you can see that that's true because see, if this constant were 0, then it's clear that you have a linear space, the set of solutions of that equation, because it's a homogeneous equation. And so if you have any two vectors that satisfy that equation, any two specific choices of the vector v, maybe better to think of the equation this way. It's like the equation is basically s dot v equals 0. So if I have a v that works and then I have a second v that works in the same equation, let's call it v prime, then because of the properties of the dot product, you can always take any linear combination of these two, and you'll still get a solution of the same equation. So it's clearly a subspace. It's closed under linear combinations. So yeah, if the constant were 0, then it would be a subspace. And the fact that the constant is not necessarily 0 just means that it's a translated image of a subspace, which is exactly what we mean by a flat. Right? A flat is just a translated subspace. So it's translated so that it doesn't have to necessarily go through the origin. So yeah, anyway, this equation denotes a flat, and it would have this dimension, because it's just one constraint on d minus r variables. So you lose exactly 1 degree of freedom from the entire space, but you'll still have d minus r minus 1 degrees of freedom. Okay, so it formally follows by the rank-nullity theorem that is the dimension of that space. Okay. Anyway, so coming back here then, when I talk about setting w1 equal to a constant, that equation is going to give some d minus r minus 1 dimensional flat in the v space, like just the space of the v axes, the span of the v axes. So it's like a hyperplane in there, among the v axes. And what I'm doing is basically slicing that hyperplane through the quadratic hypersurface given by this equation in the blue box. And I'm looking at the cross section. And that cross section is going to also be a quadratic hypersurface, because all it is these quadratic terms right here, all of these like pure square terms, set equal to a constant, namely whatever constant I plugged in for w1, and then I can move the q over to the other side and absorb that in there. So what that gives me is the equation of a quadratic hypersurface in r dimensions now, just exactly r dimensions, because now there's only r variables, u1, u2, up to ur. But that quadratic hypersurface is not parabolic anymore, because it doesn't have any linear terms. It just has quadratic terms and then a constant term. So you see that we've reduced back to case 1, just in a different dimension. If you look all the way back to case 1 was the case where you have only pure square terms set equal to a constant. There are no linear terms. Now, so we've basically reduced back to that case, right? And I even said it's like in dimension r, not necessarily dimension d. That's why I did this, because you can now see why I did this, because back over here, when I set w1 equal to some constant, then I get exactly that. I get just exactly r such terms, pure square terms. So I'm really looking at some quadratic hypersurface in r dimensions only. And what happened to the remaining d minus r dimensions? Well, one of them is parabolic. That's w1. That's like the w1 direction. And then the remaining directions, the w2 direction, w3, the quadratic hypersurface is cylindrical with respect to those. Okay, great. So this brings us back to case 1. If we can understand the shape of an equation of this type, where there's only pure square terms and a constant term, then we'll basically have everything we need to understand the geometry.